Quadratic equations are used to model several different types of situations. Some they model nearly perfectly, and others they model only over a certain period and then experience model breakdown. We'll be taking a look at both of those examples. But before we take a look at examples of quadratic models, there's some important concepts in quadratic models that we need to remember. Number one, it's always very important to identify what your independent and dependent variables are. Number two, whenever you're asked to maximize or minimize, this implies finding values at the vertex, because we remember that a parabola either opens up or down. In the case of it opening up, the minimum value, the vertex is the minimum value. In the case of it opening down, the vertex is a maximum value. So in either case, if you're maximizing or minimizing in the context of a quadratic model, it's important to remember that that implies you're finding values at the vertex. Lastly, the value of c. The value of c in the equation y equals ax squared plus bx plus c is what we call the initial value, the y-intercept. In some cases, that value is significant in that it communicates specific value to us, specific information to us. We'll take a look at what context that comes up in a little bit. So let's dive into our first example of quadratic equations or quadratic model. So this first example has to do with the flight path of a projectile through the air, in this case a baseball. So the quadratic function h of x equals negative 0.004 x squared plus 1.12x plus 3 models the height in feet of a hit baseball, that's in h of x, after it has traveled a horizontal distance of x feet. So we have two different variables here, x and h of x. X is horizontal distance. H of x, h is our height, which you could understand as vertical distance. The question is this: what is our independent variable? What is our dependent variable? Because it's written in function notation here, h of x, it communicates to us what the independent and dependent variable are. The independent variable is x, which equals horizontal distance. Conversely, our dependent variable is the variable h. We can write it as h of x in function notation if we want, and h of x is equal to height. In other words, the height of the ball is dependent upon how far it has traveled horizontally. It is important to include units. Horizontal distance is in feet, and our height is also in feet. Important to keep that in mind. So with those two variables identified, let's move on and now answer the next question about our quadratic model. It says this: what was the height of the baseball after it has traveled 40 feet horizontally? So we're asked to find the height after it's traveled 40 feet horizontally. The important piece in regards to identifying dependent and independent plays itself out in this problem, because we are given some information and then asked to calculate some information. In this case, we're given that it has traveled 40 feet horizontally. Up here we defined, or we identified, our horizontal distance as our independent variable x. So we're being told that x is equal to 40. In this problem, it's also asking us what was the height. That's the piece that it wants us to find. Height in this case is h. Well, h of x, we just identified that the known quantity is that x equals 40. So in essence, this problem is asking us to find what is h of 40. In other words, what is the height after it has traveled a distance of 40 feet horizontally. That's our x. So h of 40 would simply mean we plug 40 in for our x's in our quadratic model. So our equation becomes negative 0.004 times 40 squared plus 1.12 times 40 plus 3. So at this point we can get a calculator out and plug this in and see what this value ends up equaling. So back to our home screen here. Let's take a look. We have negative 0.004 times 40 in parentheses squared plus 1.12 times 40 plus 3. It gives us a height of 41.4 feet. 41.4 feet. So after the ball had traveled 40 feet horizontally, the height of the ball was 41.4 feet in the air. Great. Let's move on to the next question it's asking in regards to this quadratic model. The next question says this: what was the height of the baseball right when it was hit? Right when it was hit. Well, there's a couple ways we can look at this problem. One way we can look at this problem is that first off, height is what we're looking for. What's the information we've been given? Well, we've been given that we want to know the height right when it was hit. Well, how far has the ball traveled horizontally right when it was hit? Well, if it's right where it was at the initial hit, we know that our x is equal to 0. That's the horizontal distance it's traveled right when it was hit. So in essence, we are being asked to calculate h of 0. h of 0 is equal to what? It's equal to negative 0.004 times 0 squared plus 1.12 times 0 plus 3. When we simplify this, we won't even need to use a calculator here, because since both values, or the value of x is 0 in these two locations, the first two terms cancel out and you end up with h of 0 equals 3. h of 0 equals 3. So the height of the baseball right when it was hit was 3 feet above the ground. Now, we could have approached this from the standpoint of understanding it in terms of an initial value. We made the statement at the very beginning that the value of c in your equation, which for us is this value here, the value of c represents your initial value in the units and label of your dependent variable. For us, it's height. So the value of c, as you notice, everything else disappears when x is 0. The value of c tells you your initial value. And the phrase right when it was hit is implying the height at the very beginning, the initial value. So we could have, instead of doing all the calculation of finding h of 0, just known that the value of c in a quadratic equation gives you your initial value. With that, let's move on to the last question using this quadratic model. The last question here states this: how far had the baseball traveled horizontally when its height was 34 feet. So again, we're asked to find something, but we're also given something. The question is, what are we asked to find? In this case, we are asked to find how far had the baseball traveled horizontally. Back up top, we had identified horizontal distance as our independent variable. So in this case, our independent variable h, which is horizontal distance, is what we're, or x, sorry, not h, x, is what we're supposed to be finding. We need to find x. This is what we do not know. However, we're given some information. We're given that the height was 34 feet. Well, height, if we go back up here, was our dependent variable. Right. So we're given that h is equal to 34 feet. If we take a look at our original model of h of x is equal to negative 0.004 x squared plus 1.12x plus 3, we are going to end up taking this value of h and plugging it in for that independent or the dependent variable. So it ends up looking like this. It ends up looking like 34 is equal to negative 0.004 times x squared plus 1.12 times x plus 3. So in this case, we're plugging a value in for the dependent variable rather than the independent variable, which means that it's not simply evaluating the right side of the equation to figure out what h equals. In this case, we need to figure out what x equals, which means we're solving a quadratic equation. Well, factoring is out of the question because of the decimals that we're dealing with. The best approach for this would be to use the quadratic formula. But in order to use the quadratic formula, we need to make sure that our equation is set equal to 0. So to do that, I'm going to subtract 34 from both sides. This ends up giving us 0 is equal to negative 0.004 x squared plus 1.12 times x, and that gives us minus 31. So our quadratic equation is now set equal to 0. Let's identify our value of a. That would be here, the negative 0.004. Let's identify the value of b. That would be this value here, the 1.12. And lastly, the value of c. The value of c is negative 31. Negative 31. Now we know that our quadratic formula says that x is equal to negative b plus and minus the square root of b squared minus 4ac all over 2 times a. So plugging in the values that we have for a, b, and c here produces x is equal to negative 1.12 plus and minus the square root of 1.12 squared minus 4 times a, which is negative 0.004, times c, which is negative 31. And all of this is divided by 2 times a being negative 0.004. So we have everything plugged in where it belongs. Now it's just a matter of simplifying. So to simplify this, we have x equals negative 1.12 plus or minus. Now I'm going to get my calculator back out, and I'm going to plug in all of the square root at once. I'm going to do it very carefully though. So I'm going to go second square root. I got to turn on first. We'll clear that entry out. So second square root, and in parentheses 1.12 squared minus 4 times negative 0.004 times negative 31. So all of that under the square root, hit enter, and we get 0.87 is what we'll round it to, 0.87. And all of that is divided by, well, if I do the multiplication in the denominator, I end up with negative 0.008. Good. Well, we're not quite done. We need to get 2 final answers out of this. So what we'll do is we'll end up getting decimal approximations for each of these. So we're going to do our negative 1.12 plus 0.87. Hit enter. We're going to divide that by negative 0.008. We're going to get 31.25. And now we have to do the subtraction. We have to do negative 1.12 minus 0.87. Hit enter. Whatever that is, divide that by negative 0.008. And in this case, we come up with 248.75. 248.75. So we have 2 solutions here. The question is, which solution is correct, or are they both correct? Let's go back to the scenario really quick to discuss. It says, how far had the ball traveled horizontally when its height was 34 feet? If we think about this, we'll actually notice that both answers are correct. If you think about the travel, let's get a base here. This is the ground. And if we then hit the ball, there's actually 2 locations at which the height will be 34 feet. It'll reach 34 feet on its way up, but then there's another point at which it'll be 34 feet in the air on its way down. So both solutions give valid answers because the ball is in 2 different locations. At 2 different locations, it's 34 feet in the air on its way up and on its way down. So we would say 31.25 feet and 248.75 feet are the 2 locations, the 2 horizontal distances at which our baseball is 34 feet in the air. The next example that we're going to work through is very similar to the first example we just finished, with some differences, specifically differences in variables. Let's take a look at this and see similarities and differences. It says the quadratic function h of t equals negative 4.9 t squared plus 52t plus 12 models the height in meters h of t of a projectile t seconds after it was launched from the edge of a cliff. The height is measured from the bottom of the cliff, which we're going to call ground level. So first things first, what is the independent variable and what is the dependent variable? Because it's written in function notation, we can easily identify t as our independent variable, which is equal to time. And identifying units, that's in seconds. Which means that our dependent variable is h. H up here is height, in meters. So height in meters. Okay, so height is dependent upon time. So this is the key difference in this function compared to the first example that we looked at here. Height is dependent upon time since the projectile was launched, whereas in the first example, height was dependent upon horizontal distance traveled. So the first example we did, the variables were horizontal distance and height. Here, no more horizontal uh, distance is represented in our function, only time and height. So the height is dependent upon time. Now we can see that this would be the case in that if you throw something in the air, the height changes over time. It increases in value and reaches its maximum point, and then it decreases in value and comes back down because of gravity. So we have our variables identified. Next, what is the height of the cliff from ground level? What is the height of the cliff from ground level? So it said that this projectile models height of a projectile launched from the edge of a cliff. However, the model says that the height is measured from what? Is measured from the bottom of the cliff, which we are going to call ground level. Well, from the previous example, we recall that the initial value is our value of c. So in our function, c is equal to 12. 12 is our initial height, which means that that is the height of the cliff from which it was launched. So we would say that the height of the cliff is 12 meters. 12 meters above ground level. So what that may look like physically, okay, is that here is ground level, and here is the cliff. And it's from this edge right here that the projectile is launched. And that value of c tells us that that cliff is 12 meters off the ground. So again, the value of c up here tells us our initial value. Next question that it's asking us is, what is the height of the projectile after 4 seconds? So again, in this type of problem, it's asking us for something and telling us for something. In this case, it's asking us for height and telling us time. It's telling us that time, t, is equal to 4. Well, if we want to find height when t is 4, that means we're looking for what the height is after 4 seconds, so h of 4. And in our case, that is equal to negative 4.9 times 4 squared plus 52 times 4 plus 12. Plus 12. So let's really quick grab our calculator here. Okay. And we are supposed to do, let's clear this out, we're supposed to do negative 4.9 times 4 squared plus 52 times 4 and plus 12. We end up with a height of 141.6. So this right here is 141.6, and the units of our height is in meters. So after 4 seconds, well, from 4 seconds after launch, our projectile is 141.6 meters in the air. Okay, this next question is an interesting question. It'll cause us to remember one of the principles that we looked at the beginning. It says this: what is the maximum height the projectile reaches? And how many seconds does it take to reach that height? Now we recall from the very beginning that anytime we were asked to maximize or minimize anything, we need to find the vertex, because the vertex is either your maximum or minimum point. So let's go through the process of finding our vertex. We know that the x-coordinate of our vertex is negative b all over 2 times a. What does this equal? Well, we know our b value is 52. Okay, from our equation, our b value is 52. Let's write those down really quick. Our a value is equal to negative 4.9. Our b value is equal to 52. And we already know that our c value is equal to 12. So back to our problem, negative b. So that's going to be a negative 52 divided by 2 times a being negative 4.9. Okay. So this is going to equal negative 52 all over negative 9.8. 2 times negative 4.9 is negative 9.8. Getting a final result for this, okay, we want negative 52 divided by negative 9.8. Enter, and we get a 5.31. We'll round it to 2 decimal places. So this is equal to 5.31. So the x-coordinate of our vertex is 5.31. To find the y-coordinate of our vertex, we simply take our x-coordinate, plug it in to the x location of our equation. So we essentially want to find what negative 4.9 times 5.31 squared plus 52 times 5.31 plus 12 is. So we're plugging the x-coordinate into our function and solving for y in order to get the y-coordinate of our vertex. So finishing that off, we end up with what? Negative 4.9 times 5.31, that gets squared, plus 52 times 5.31 plus 12. Enter, and we get 149.96. 149.96. 149.96. So we now have our x and our y coordinate of our vertex. So our vertex coordinate point is 5.31, comma 149.96. Well, back to the problem, it says this: what is the maximum height the projectile reaches, and how many seconds does it take to reach that height? Well, if we remember, we already identified what our independent and dependent variable are. Well, for us, instead of t and y, x is the generic independent variable, and we knew our independent variable was t for time. And y is the generic dependent variable. We already know that in our case, our dependent variable is h. So we know that the maximum height our projectile reaches is 149.96 meters, and it takes 5.31 seconds to get to that height. The last question we want to answer in regards to this question is down here. It says this: at what time will the projectile be 90 meters above the ground? At what time will the projectile be 90 meters above the ground? Well, we're given some information and we're asked to find some information. At what time? We're looking for time. Will the projectile be 90 meters above the ground? We're given a height. So we're given that h is equal to 90. And time is what we're looking for. We don't know what time is. So what we want to do is we want to plug 90 in for h and solve for t. What this ends up looking like is we plug 90 in for h, so that's 90 is equal to negative 4.9, write it just a little different, 4.9 times t squared plus 52 times t plus 12. And here's the equation that we need to solve for t. It's a quadratic equation. Because of the numbers that I see, I'm not going to attempt to factor it. I cannot solve by the square root property, and completing the square would be relatively difficult. So I'm going to go straight to the quadratic formula. But in order to use the quadratic formula, we remember that we have to have our equation set equal to 0. So I'm going to start by subtracting 90 from both sides of my equation. And that ends up giving me 0 is equal to negative 4.9 times t squared plus 52 times t, and that would end up being minus 78. So we've got our equation here set equal to 0. I'm going to identify the a, b, and c right here real quick. So my a value is equal to negative 4.9. My b value is equal to 52. And my c value is equal to negative 78. Well, we know that the quadratic formula tells us that if we have a quadratic set equal to 0, then our variable, in this case t, is equal to negative b plus and minus the square root of b squared minus 4ac, all divided by 2 times a. So we want to go ahead and plug our a, b, and c values into this, and it produces t is equal to negative 52 plus and minus the square root. Let's see, that's going to be 52 squared minus 4 times a, which is negative 4.9, times c, which is negative 78. Let's extend that square root, and all of this is divided by 2 times negative 4.9. Okay. What I'm going to do is I'm going to go ahead and simplify everything underneath the square root symbol. So go in here, well, with the square root symbol. So I'm going to go square root, let me turn this on. I'm going to go square root of 52 squared minus 4 times negative 4.9 times negative 78. Enter. I get 35.13. 35.13. So t is equal to negative 52 plus and minus 35.13, all divided by 2 times negative 4.9 is negative 9.8. Okay. At this point, we can split this up into 2 separate equations. I'm going to bring my calculator over here. And we are going to end up doing negative 52. So we're going to do the addition part first. So negative 52 plus 35.13. Get an answer for that. And we're going to divide that by negative 9.8. We end up with 1.72. So t is equal to 1.72, or now we need to do subtraction. So it's going to be negative 52 minus 35.13, and divide that by negative 9.8. We end up with an 8.89. 8.89. So we end up with 2 answers. T is equal to 1.72 or T is equal to 8.89. The question is, which one of these is the correct answer? In fact, both are the correct answer because there's two locations in which our projectile is 90 meters in the air. On the way up, so here's our cliff, on the way up and on the way down. If 90 meters is right here, there are two locations, right, at which we are 90 meters in the air, on the way up and on the way down, as we've said. So both solutions for T are correct. The projectile is 90 meters in the air at 1.72 seconds and at 8.89 seconds. We want to work through one more example of quadratic modeling that is a little bit different than the two we've seen already. In the previous two, we were given our function. Here, we're given data in which we'll have to use to find a function. It says this: the data below shows the average monthly temperatures of Salem, Oregon for January through May, where January we're calling month 1 and May obviously is month 5. So you can see this in the table in regards to the months here represented as numbers so that we can work with them, and then temperatures in Fahrenheit, the average temperature in that month. So the question is this: as we start off, what is the independent variable and what is the dependent variable? One way to determine this is to ask yourself, is the temperature dependent upon what month it is? In other words, does the temperature change as you go from month to month, or does the month change as you go from temperature to temperature? In other words, is the month dependent upon what temperature it decides to be? Well, no, the month happens no matter what the temperature is, so we would say that the temperature is dependent upon what month it is. Therefore, our independent variable will be month, or months, and our dependent variable will be temperature in degrees Fahrenheit, because temperature is dependent upon what month it is. But here's how we're going to find our model. It says this in part C: use the quadratic regression command on your calculator. Using it, find a quadratic model where T of X is temperature in Fahrenheit and X is month. Let's go ahead and put X here for month and T for temperature now that we have our variables identified. So we want to go ahead and use the quadratic regression on our calculator. So let's get our calculator up here. Now, to do quadratic regression or any type of regression on our TI calculator, we first need to go to Stat. So we hit our Stat button, and the first options that are selected are Edit, Edit, and that's where we want to go, because it'll take us to our L1, L2 columns where we can fill in our data into the calculator. So L1, we want to be our independent variable. Well, over here we have identified months as independent variables. So what I'm going to do is I'm going to go ahead and type in 1, enter, 2, enter, 3, 4, and 5, because those are my independent variables representing months: January, February, March, April, and May. I'm going to hit my right arrow to go to column L2. L2 is where the corresponding dependent data points go. In this case, dependent is our temperature in degrees Fahrenheit. So I'm going to start by putting in 40. Next is 53, 64, 72, and 77. So we have our data in our calculator now. Now we want our calculator to do a calculation with it. So we're going to go back and hit our Stat button again. But this time we're going to go hit our right arrow over to the Calc menu. Several options in here. The option that we're going to select is option number 5 that says Quad Reg. That stands for quadratic regression. With option 5 highlighted, hit enter. It correctly identifies our X list as L1 or Y list as L2. That's independent, dependent. The frequency list, and next option, the store regression equation, don't matter to us at this point, so we're just going to scroll down to calculate and hit enter. And as it does that, notice we have y equals ax squared plus bx plus c, and it gives us the value of a, b, and c. So it's telling us that the value of a is negative 1.36. So a is equal to negative 1.36. Our value of b is 17.44. And lastly, our value of c is 23.8. So it's telling us our three coefficients for our quadratic model. We know our quadratic model in standard form is y equals ax squared plus bx plus c. For us, though, we know our dependent variable is t, so it's going to be t of x is equal to a. We have identified a as negative 1.36 from our quadratic regression, and that's x squared. Plus our b value, which is 17.44 times x, plus c, which is 23.8. So from the quadratic regression in our calculator, here is our model. So we can now use this model to make calculations, to make estimates and predictions. Let's take a look at this first one. It says this: what is the estimated temperature in November according to this model? Well, in November, what data does that actually give us? Well, first let's identify what they're asking us for. They're asking us for temperature, and they're giving us the month, November. The question is, November gives us what? Well, the month is our x variable, so November gives us that x equals, well, if January was 1, February was 2, if we keep counting and get to November, we find that x is equal to 11. So we're given that x is equal to 11, and we're supposed to find our temperature. So using our model, it's asking us to find T of 11, the temperature when x equals 11. Well, that equals for us negative 1.36 times 11 squared plus 17.44 times 11 plus 23.8. So we plugged 11 into our independent variable x, and now we simply simplify the right-hand side of this equation to find the temperature in November. So that's negative 1.36 times 11 squared plus 17.44 times 11 plus 23.8. Hit enter and we get a 51.08. So we are getting that the temperature in November is 51.08 on average degrees Fahrenheit according to our model. Great. The last question that we want to answer is down here in part E. It says, what month is the estimated temperature 70 degrees Fahrenheit? In what month? So in this case, we're being asked for month, and we're being given temperature. So we want to find X, which represents month, and we're given T, which is temperature. So we're going to go ahead and plug 70 in for our T. So that gives us an equation that looks like 70 is equal to negative 1.36 times x squared plus 17.44 times x plus 23.8. Oh, there we go. So here's the equation that we're supposed to solve. Again, we have a quadratic that we're needing to solve. Because of the setup of the quadratic and the fact that the coefficients are decimals, best way to approach this again is going to be the quadratic formula. But in order to be able to use the quadratic formula, our equation must be set equal to 0. So to get that, I'm going to subtract 70 from both sides of the equation. That ends up giving me 0 is equal to negative 1.36 times x squared plus 17.44 times x, and 23.8 minus 70, 60, 50, that's going to be minus 46.2. Minus 46.2. So we have our equation here of 0 equals negative 1.36 x squared plus 17.44 x minus 46.2. Let's identify our a, b, and c. We have here that a is negative 1.36. Our b value, 17.44. Our c value, negative 46.2. So with those identified, we know that they end up getting plugged into the equation. X equals negative b plus and minus the square root of b squared minus 4ac all over 2a. So plugging our values in, we end up with x is equal to negative 17.44 plus and minus the square root of 17.44 squared minus 4 times a, which is negative 1.36, times c, which is negative 46.2. And all of that's divided by 2 times a, which is negative 1.36. So I'm going to start by simplifying everything that's underneath the square root along with the square root. So that gives us second square root. I'm going to go 17.44, square that, minus 4 times negative 1.36 times negative 46.2. Close that off. And you end up with 7.27. 7.27. So x is equal to negative 17.44 plus and minus 7.27. Let me check that one. Yep, 7.27, yep. Divided by, if we do 2 times negative 1.36, I believe that ends up giving us negative 2.72. So we now need to find decimal approximations of both answers in here. I'm going to come up here to do that. So we first need to start with negative 17.44. I'm going to add, for the first time, 7.27. And then divide that by negative 2.72. For that first one, I'm getting 3.74. Okay, so 3.74. And then for the next one, we have to do subtraction. So negative 17.44 minus this time 7.27. Get a solution for that and divide that by negative 2.72. And we get 9.1. Well, because these represent months and months are represented by whole numbers, I'm going to say 4 and 9 are the months. Well, these months for us, 4 would be January, February, March, April, and 9 would be October. I'm sorry, September. So we have that our equation is giving us that the average temperature is 70 degrees in April and September. Can both answers be correct? Yes, because we know that temperature peaks in the summertime. And if we go back up to our data at the very top, we'll notice that in April, 72, in May, 77. So it is going up. We anticipate in June that it'll be higher, in July, and then it'll start coming back down. Now we'll notice, did our estimates perfectly match our data here at the beginning? Well, no, it didn't, because it says that the average temperature in April is actually 72, not 70. But again, our model is not perfect. It doesn't model the data exactly. Furthermore, we'll probably end up with model breakdown, because we know that a quadratic looks something of this nature. And we know that once the year comes to an end in December and you get back to January, that the temperatures will actually start going back up. In a quadratic model, you're going down forever. You never come back up. So in this case, a quadratic model may only be good for modeling over a short period of time. In fact, it is only good over a short period of time. If you want to model continuously over the years, I'm probably going to need a different model. So we will easily experience model breakdown in this example, but it does do a good job modeling our confined data set.